morning, everybody. This is Jon Konings. I'm the Senior Regulatory Specialist with ESC Spectrum, and I'm here to give a presentation today on Air Quality Regulations 101, as we call it, for parts 60, 63, and 75. This is an introduction to these air quality regulations that the services and systems provided by ESC Spectrum typically are trying to serve or help our customers demonstrate compliance with. So there are three major regulations that we'll talk about today, and it's intended as an introduction to these topics. We don't expect that you know very much about them, so we're trying to lay the foundation for your understanding and for your development. Okay, today's agenda, we're going to talk about regulations and equipment, and it's going to be broken down into three major groups. First is an overview of the regulations that we're talking about. Next, we're going to talk about boilers and combustion turbines and these emission sources and how they contribute to the emissions that our systems are monitoring. And then we're going to talk about the petrochemical industry and how it not only is similar to the regulations for boilers and combustion turbines, but also different. And so we'll hopefully be able to educate you as we move ahead today. First one is the overview of the Part 60, 63, and 75 air regulations. Part 75 really is for the acid rain program. We'll talk a little bit more about that as we proceed. The Part 60 regulations, also called the New Source Performance Standards for Stationary Sources. That sounds like a lot of language, but what it really is industry-specific regulations that talk about the types of air emissions that are released by the combustion sources found at these sites. There are 90 different subparts in the Part 60 rules, and there are 6 non-hazardous air pollutants that we are primarily concerned about. So we'll talk about those a little bit more detailed as we move forward. The last regulation is the Part 63 regulations, and these are the National Emission Standards for Hazardous Air Pollutants, or source categories. And hazardous air pollutants, we also call those HAPs. There's 133 different HAP regulations, and there's 187 different HAPs that are currently being regulated. And we're not really going to go into details on those other than in general concepts, what kind of regulation, what kind of pollutants we're talking about and why they're important. So with that being said, let's move into the first topic. The industries we serve. Typically, we serve just about any industry that burns a fossil fuel, and from the combustion of those fossil fuels, air emissions are released. This is typically from electric utilities, petrochemical refineries, and chemical processors, even as far as biomass facilities, incinerators. So just about anybody who burns a fuel comes under some form of air regulations and are typically required to monitor those emissions to make sure that they are not violating their permits or any of the emission regulations. Later on in the presentation, we'll talk about the differences between coal-fired units, gas-fired turbines, and petrochemical facilities as well. The Part 60 regulations, and here's just a listing of some of the Part 60 regulations that we typically run into. For boilers, the most common ones are the subpart D, DA, and DB, and these are typically electric utility steam generating units or industrial and commercial steam generators of various sizes. Also for combustion turbines, the most common regulations we run under there are the stationary gas turbines for subpart GG and quad K. And subpart GG are very simple combustion turbines, where quad K are now combustion turbines with duct burners and heat recovery steam generators. So we'll explain a little bit further about those as we move forward as well. Part 63 regulations, again, we've got a listing here of the ones that are most commonly encountered. One is the 5D, subpart D, which are the industrial, commercial, and institutional boilers. And there's 5Us, which is the electric generating utility, Part 63 subpart. So you can see there's lots of different regulations that are out there. They all are somewhat similar, but they all are different and independent. And that's why they are so industry specific. So we'll talk a little bit more about that as we move forward. The regulations for Part 75 are much more specific. that deals specifically with acid rain. This was created in the 1990s by the Clean Air Act amendments of 1990, was authorized by Congress to reduce the acid rain formation that was occurring from electric generating power plants. Specifically, the SO2 emissions and the NOx emissions, when released into the air, combined with moisture in the air, i.e. rain, and fall back to Earth as acid rain. And so there's been a tremendous reduction in the amount of acid rain that's been released and falls back to the Earth in the last 25 years. We'll talk a little bit about that as we move forward. The type of fuel that your facility burns or unit burns and the amount of operating time per year dictates the types of monitoring that is required. For example, if you're a coal-fired boiler and you're operating 50% or more of the hours in a year, you're typically going to have full SEMs, meaning you're going to have a NOx, an SO2, a CO2, maybe a CO monitor, a stack flow meter, opacity monitors, a wide range of monitors. Where if you're burning oil or natural gas, which are typically cleaner fuels than coal, then you can reduce the amount of monitoring that you are required to do. You might be doing fuel flow monitoring or metering, and then have only a couple of monitors like NOx, O2 or CO2, and maybe a CO monitor. Lastly, there are also what they call peaking units. And these are units that run less than 10% on capacity per year. And in this, for the peaking units, you can do what's called NOx correlation testing. And this is testing in which you develop an emissions curve of your NOx emissions over the operating range of your unit. And that emission curve is built into your gas system. And as the unit is tested, you develop that curve. And then that curve is used after the testing is completed to estimate what your NOx emissions were during that operating hour, and are used to calculate and accumulate your total NOx emissions. Lastly, the final method for reporting your emissions is called a low mass emitter. These are units that run very infrequently, maybe 100 hours or less per year. And these units, because they operate so infrequently, to reduce the monitoring burden on them, they are allowed to either test and develop specific emission factors, or they're allowed to use especially to develop default emission factors. And therefore those default emission factors, or those emission factors from that testing, is used and reported for each hour that the unit operates. Then those hourly operating numbers are used to accumulate the annual and quarterly totals. And so low mass emitting units really don't even have any monitors per se. So now you can see by these four examples that the amount of monitoring that's required, the amount of investment that's required, the amount of work that's required varies with the type of fuel that you burn and the number of operating hours that that unit operates in during each calendar quarter. Moving on, how are these three regulations similar? Well, all three of them are similar because they all have a foundation into what we call 1 hour averages. For each minute that the unit is in service, the monitoring systems measures the emissions that are desired and develops a minute average. Those minute averages are used to create a 15-minute average, and each of the 15-minute averages recorded in an hour are used to come up with an hourly average. The same methodology for developing these hour averages are used both by Part 60, 63, and 75. Each of these regulations require that these CM systems be certified, and there are procedures outlined in each of the regulations on how to certify them. Each regulation also requires that there are daily what they call quality assurance checks. These checks are typically done each day to make sure that the accuracy and reliability of the monitors is being utilized, and that they are operating repeatedly and accurately each and every day. And each regulation also requires that some sort of quarterly or periodic reports be submitted to the agencies. Moving on, there's also annual requirements, meaning that every 12 months or so, you have to perform what's called a relative accuracy test audit. A relative accuracy test audit is a comparison between the emissions recorded by your monitoring system versus another monitoring system brought in by a stack testing company. Stack testing company are brought in from the outside. They use special reference method equipment that is approved by the US EPA, and you do a side-by-side comparison of the performance and measurement levels of your system versus the stack testing system. This relative accuracy test is a series of comparisons and lasts between 3 and 8 hours in duration, and hopefully it proves that the accuracy of your system is very close to the stack testing or reference system. In addition, we also have other events that we're concerned about. Like, for example, if excess emissions are recorded, meaning your hourly values or multiple values are recorded above the emission standards or emission limits outlined by the regulation or your permit, that's not good. Excess emission periods mean that you are emitting more pollution than you should be, and something's wrong. Another occurrence is also called downtime. And downtime occurs when the unit is in service and operating and making emissions, but your monitoring system is not working correctly and recording what the emissions are. So the regulations basically say every minute that the system is in service, that the emission source is creating the emissions, and you must be monitoring those emissions. And when you're not monitoring them correctly or accurately, that period of time is called downtime. Like I said before, all 3 regulations have emission limits or standards that they impose. And they can also have mass limits. Mass limits meaning pounds per hour or tons per day or other mass standards. The duration of these standards can be short or long. For example, some limits are as short as 6 minutes. Some averages are as long as a whole year. So it depends upon the nature of the pollutant, depends upon the type of device that you're monitoring that determines the duration of these standards. And again, like I said before, if data shows that the emissions are over the limit, it's called an exceedance, and your facility can actually be fined or forced to be shut down if you consistently have these exceedances. Also, the regulations are define how compliance is determined. And compliance means that you are demonstrating that your facility is operating in a way that does not exceed the standards. So the continuous emission monitoring systems are typically used to demonstrate that you are in compliance with these emission standards. Now, these emission standards are also defined in the operating permits. Each facility in the last 25 years has been required by federal law to obtain an operating permit. And the operating permit is the legal right for that facility to operate. Without an operating permit, the facility is not allowed to operate. And you'd be surprised to know the number of types of facilities that are required to have operating permits. Things like gas stations, because they have gasoline, and that's a hazardous, can be considered sometimes a hazardous air pollutant. They are required to have air permits. A bakery, because of the ovens that they have and the fuels that they use to heat their ovens, they have an operating permit. Dry cleaners are another example of a facility that has operating permits. So not necessarily is it our operating permits limited to power plants and petrochemical facilities, but a lot of the various businesses we see each and every day have the requirements for operating permits as well. As I mentioned before, the regulations and the permits require that you demonstrate compliance with the emission requirements of your permits. There's 3 different types of compliance that we're going to talk about very briefly. First off is continuous compliance, where data is recorded continuously, taking data from monitors and sending it to a data acquisition system where the data is continuously recorded. The second type of compliance is periodic compliance. And this is when data is recorded or written down on a periodic basis. You might be required on your permit to do a walk around of your facility and to make sure that everything is working correctly. And you might be required to do that once a week. And so this once a week is an example of periodic compliance. And then there is also called indirect compliance. That's because sometimes there is no direct way to measure a particular pollutant of concern. And so if that pollutant is being controlled by a pollution control device, then the operating conditions associated with that pollution control device or the process itself is typically monitored to make sure or to demonstrate that it is operating and that it is operating properly. And so you might be forced to record the temperature, the pressure, the pH, or the water injection rate, for example, of a pollution control device to demonstrate indirectly that you are in compliance. How are these three regulations are different? Well, one way they are different is that Part 75 addresses data downtime or data holes differently. Remember I said before, downtime occurs when the monitoring system is not recording accurate data as it should be during all periods of time that the emission source is in service. Part 75 handles these data points, these data gaps a little differently in the fact that it goes back into your historical emissions database, and under similar operating conditions that are occurring now, it will use historical data to estimate and fill in that data gap with what it believes is representative data. The algorithm that actually does this calculation to determine a replacement value, that algorithm is tested by the EPA and is approved by the EPA. So again, it's done on an hour-by-hour basis using an approved EPA algorithm, and it uses historical data. So in that way, Part 75 is different than Part 60 and Part 63. Those two systems report the downtime, where Part 75 fills it in with historical data. Let's talk about operating permits again. I mentioned them a little bit earlier. Operating permits really came into effect starting in the late 1990s. They were initiated by the Clean Air Act amendments of 1990, but they originally began coming out in the late 1990s. And the purpose of the operating permit is to have one document covering any regulations that are on that facility, dealing with air regulations, I really should say. They have one document that contains everything that an operator of that facility needs to know about what are the requirements for operating that facility. Tells them what they can do, what they can't do, and if something happens, what sort of response the government air quality agencies are looking for from them. So it's a single document that incorporates all the air quality regulations and information into one place. Let's move on to our second topic, which is boilers and combustion turbines. This is where you burn a fuel, the fuel releases heat. That heat is used to typically create steam. That steam is used in a process to operate equipment, whether it be to run some pumps or to use or spin a turbine generator to make electricity. But typically boilers and combustion turbines take the fuel, burn that fuel, release the energy, and create a product. So like I said before, when you burn a fuel, you make emissions. And when a carbon-based fuel is burned, the carbon is converted to carbon dioxide or CO2. Unfortunately, the fuel could contain other undesirable contaminants, such as heavy metals like mercury, selenium, chlorine, plus many, many more. And these other contaminants, even in very low concentrations, can be harmful to man and other living creatures. So you can see here on this diagram, this picture, that's probably a 1950s version of a power plant, the big tall stacks for releasing the flue gas into the environment. There's also lots of equipment on the back end for trying to capture or control those emissions. Let's talk a little bit about the pollution control equipment. Lots of plants add pollution control equipment on to reduce or capture their emissions. And this is trying to reduce the emissions below those limits that are found in their permits. And there are four main pollutants that the Part 60 regulations are focused on. The first are particulate, or as you typically think of it as smoke. Those particulates inhibit the ability to see through the flue gas stream, and so we call that smoke typically. But there are specific pollution control devices that are built and used to capture those particulates. First are cyclone separators. Second are bag houses, and bag houses are no different than the vacuum cleaners that you use in your home to vacuum the dust and particulates that are found in your carpets. And so these bag houses that power plants use are much, much, much bigger and have tens of thousands of bags in them to capture that particulate. Two other devices that are used to capture particulates is one's called electrostatic precipitator, And this uses a static charge to attract and capture those particulates. And the last device is called a wet scrubber. Typically, we'll show you a picture coming up where you'll see what looks like a white plume coming out of a stack. You might think that's a white smoke. Well, it really isn't. What that really is the water vapor that the wet scrubber uses to capture the particulates. Moving on, the other two pollutants that the Part 60 are concerned about are NOx and CO, which is carbon monoxide. And here we have chemical reactors that convert the NOx to oxygen and nitrogen gas and further oxidizes the carbon monoxide into carbon dioxide. And these two types of reactors are catalytic reactors and then selective catalytic reactors, which are very specific to the type of pollutant you're working against. And the last pollutant we're talking about here is sulfur dioxide. And sulfur dioxide, when released into the atmosphere, combines with moisture to form sulfuric acid, or again, as we said earlier, acid rain. And so there are three main types of control devices for SO2. You have dry sorbent injection, which is where you inject baking soda into the flue gas stream. It mingles with the CO2, the SO2, captures it, and then a baghouse is used to capture those particulates. Or you have wet scrubbers, like I mentioned before, which uses a wet slurry, and that's mixed, that's blown into the flue gas stream, and again, it combines with the SO2 and captures it, and then the water droplets are captured, and therefore the SO2 concentration is reduced. Then you can also have what are called fluidized beds. And again, it's a chemical reaction system to capture the SO2. So these are the four main pollutants that Part 60 regulations are focused on. Moving on, let's talk about those sources of those emissions. Let's talk about boilers and combustion turbines and how they work. And boilers are used to burn a fuel, like I said before. That can be coal, gas, oil, wood, tires, lots of different sources of fuel are out there. And it releases its thermal energy, heat, to boil water and make steam. And so this is just a picture or a graphic representing a boiler where water is heated and converted into steam. The steam is directed to a turbine, and that causes the turbine to spin. That turbine is also connected to a generator, and that spinning generator and turbine set allows electricity to be produced. And so we're going to see a couple of examples of boilers coming up. This is a diagram of a modern coal-fired boiler with all of its pollution control equipment. You can see towards the left side over here is what they call a steam generator, which is like that furnace we just talked about. And it really is a four-sided boiler, which the four walls all have hollow tubes of water in them, where the water is heated and turned into steam, and the steam goes to that turbine generator set, like I mentioned, to make electricity. All the other equipment on the back end of the boiler is used to process that flue gas, as it's called, whether it's various fans, primary air fans, forced draft fans. You can see here it talks about a dry scrubber. Again, it's a calcium carbonate injection into a baghouse over here, where the calcium carbonate mixes with the sulfur dioxide, and those particulates are captured here in the baghouse. And then from there, it goes through these induced draft fans, meaning it pulls the air through, and then it goes up the stack and is emitted out the stack into the ambient environment. And you can see these boilers can be quite large and quite complex. Here's a picture of the side of a cutout of a boiler, and these actually are two boilers. These boilers were probably built in about the 1950s. These boilers are about 40 to 60 feet wide and deep, and are approximately 80 to 100 feet high. And so these are two examples of mid-sized type boilers that were built probably in the 1950s. Here's a simple diagram of a steam turbine. You can see that the steam is made, comes in on the left side and passes over the blades of the turbine and tries to spin the turbine, and then the steam goes out the outlet. As that turbine spins, it's on a shaft. That shaft is connected to the electric generator, and as that electric generator spins, it creates electricity. So this is how you take steam and make electricity. It's a very simple diagram of a turbine generator set. Here's a photograph of a modern turbine generator set. It's my opinion or my guess that this looks like about the 600 megawatt unit, which is 600 million watts of power is being produced. This area down here, the far end, is where the steam turbine comes in and passes through the turbine, various stages of the turbine. I'm going to guess there are probably 12 stages to the turbine to capture all the energy they can from that steam. And this section closest to us is where the generator is actually located. So this all is in service, humming away. It's not quiet, it's quite loud. These are very, very large machines. Moving on, let's talk about a combustion turbine, or CTs. A simple combustion turbine really is a jet engine from a plane mounted in a frame, and then the exhaust gases are blown across the turbine generator set to spin that turbine generator set to make electricity. For a simple combustion turbine, gas or oil is burned as the fuel, and the exhaust again causes the turbine to spin. After the exhaust gas passes through the turbine, the hot gases are vented into the atmosphere, where unfortunately, under these types of turbines, a lot of the thermal energy is wasted. And so nowadays, we do it differently, and I'll explain that here in a minute as well. But moving on, here's a diagram of a simple cycle combustion turbine. That you either have oil or natural gas, a fuel, that is introduced into a combustion chamber right here in the middle of the diagram. That combustion chamber causes in that combustion chamber, the fuel is burned, and those exhaust gases are vented or directed across the turbine to spin that turbine and out the chimney, out the exhaust stack. At the same time, that turbine is connected by a shaft to a compressor. So as the turbine spins, the compressor spins, and it draws in outside air and compresses it so that there's even more air, and a hotter combustion chamber is the result of that. And so as those hot exhaust gases spin the turbine, that turbine again is connected by a shaft to a generator, where again, electricity is made from the generator. This is a picture of a simple turbine generator. The actual jet engine is located inside the blue building. Again, like we said before, the combusted fuel spins the turbine at very high speed, and it's connected to a generator where electricity is created. This diagram actually shows 4 combustion turbine sets. And you can see right here in the middle of this picture, this big opening is where the air is drawn in through air filters to filter out particulates or anything else like that. The air is routed down into the actual combustion turbine down below, and then it just turns and probably goes through some catalytic converters and other pollution control equipment before it comes out and it exhausts out this big square duct back here. So you can see there actually are 4 sets of these combustion turbines. And it is not uncommon to see multiple combustion turbines located on a single site. A 4-pack like this is very common. The most that I've ever seen at a single site is 64 combustion turbines at one site. Combined cycle combustion turbines, these are a little bit more complex than a simple cycle. As I said before, the hot gases pass through the first turbine generator set, and they're still quite hot, probably 800 to 900 to 1,000 degrees. They contain a lot of energy that normally is lost when it is vented off. But now it is routed through a heat exchanger to make, and in that heat exchanger, again, water is heated up to make steam, and that steam now is routed towards a second turbine generator set. And that second turbine generator set makes additional electricity. And so by the time the exhaust gases leave the heat exchanger, temperatures down around about 150 degrees, down from the 900 or 1,000. So they've extracted a lot more energy out of that flue gas and are making a second round of electricity. And the remaining energy makes it much more efficient and much more cost effective than the simple cycle turbine. You're going to ask, why would people have simple cycle turbines? Well, they can quickly come up to speed and quickly can begin generating on a moment's notice. I know of simple cycle combustion turbines that can be started and be at full operating capacity within 15 minutes. Combined cycle combustion turbines like this one here, because of the heat exchanger and because of the other ways it operates, takes much longer time. It may take 8 or 10 hours to be started and to reach full capacity. So it's not uncommon for a generating company to have both simple cycle, quick reacting combustion turbines, and then much more efficient combined cycle and slower reacting combined cycle turbines available. Let's move on to the third and final topic, petrochemical industry. There we have some kind of unique things that they do that we need to talk a little bit about. Let's talk about flares and fence line monitoring. Here's a picture of a petrochemical facility, and that white plume you see there really is not smoke. It's probably water vapor from a wet scrubber, where they remove probably 99% of the sulfur dioxide or any other pollutants, and therefore that white plume is really a very clean plume. It has just water vapor. As we said before, petrochemical plants use a wide range of devices to process the hundreds of different chemicals they are dealing with. The actual emissions of concern are dependent upon the raw and refined materials they are handling and processing in these pieces of equipment. So there's a wide variety of emissions that a petrochemical facility has to worry about as opposed to a boiler or a combustion turbine. Part 60 and 63, in retrospect, Part 60 regulations are simple and much more straightforward compared to Part 63. Part 60 facilities are typically focused on making power, whether that be steam or electricity. And to getting the facility, there may be between 1 to 50 sources located on that property. Where Part 63 regulations, are said before, are much more complicated and much more challenging. That's because there's a much wider variation in the type of materials being handled, things that are being burned and processed and treated and things like that. This means the types and sizes of equipment can vary greatly. And for a given petrochemical facility, there may be thousands of different emission sources that an operator of that facility has to worry about. So there are really kind of night and day contrasts between Part 60 facilities and Part 63 facilities. For petrochemical facilities, there are unfortunately some undesirable emissions that they have to deal with. And frequently, petrochemical facilities use flares to destroy those hazardous chemicals that are present in case there's an upset in the operating condition. Some upset operating condition occurs, and they need to vent those emissions off. And to make sure they're not hazardous, they run them through a flare, and the flares are used to destroy those hydrocarbons. So the duration and the temperature of these flares is continuously monitored to make sure they are working when needed, that they are working properly, and that they are effectively doing the job they are intended. And so monitoring of the temperature of the combustion zone of the flare is an example of indirect compliance. You don't know that the hazardous pollutants have been actually destroyed, but it is presumed through testing that if the flare reaches a certain temperature and maintained at that temperature, that combustion process will destroy those hazardous pollutants and not allow them to be released into the environment. Let's talk about one new round of monitoring that has come to the petrochemical industry in the last 5 years. Started in 2017, sites were required to set up monitoring systems along the perimeter of their plants to monitor the ambient emissions in the air. What we're talking about here is measuring the amount of benzene as a typical hydrocarbon that is being allowed to escape from your facility. And so this network of monitoring sites are along the perimeter of your facility, and the number of sites is determined by the length of the facility. Remember, some of these facilities are quite large, where they could be square miles. And so you might have a monitoring piece of equipment every 500 feet or so. And you might have several hundred of these monitors located throughout your facility. And they actually suck in the ambient air, and they measure the amount of air that is sucked in, and they might be sampling for, say, 10 days to 2 weeks. And after that period of time, the sampling canister is swapped out for a new one, and you continue to continuously sample the ambient air. And so that canister that has now captured whatever pollutants were there is analyzed, and from that analysis, they can determine an average concentration during that entire sampling period. And then combining this information about the average concentration of benzene during that period, they also record the wind direction and the speed of the wind. And this is being done to determine that if this benzene is present, where is it coming from? Is it coming onto your property from an outside source? Or is it coming from your property and leaving your property and now going into the ambient environment? So I personally have never operated one of these fence line monitoring systems. I've read about them, I've heard about them, I've heard people complain about them and how difficult they are. But like I said, they've been around for a couple of years, and I believe they will probably improve in their reliability and their accuracy as they go forward and people get more experience under their belt with them. So now we're coming to the end. I just want to wrap up here and leave you with a couple of takeaways. As we said, for these three major types of air quality regulations, there are similarities between all three of them, and there are differences. And sometimes those differences can be especially challenging. Combustion turbines and boilers create hazardous emissions along with the electricity they produce. And it's important for the health and safety of the people surrounding our facilities that we stay in compliance with the emission standards and limits that are found in the regulations and the air permits. The petrochemical industry faces compliance regulations that are both similar and different from the power generation industry. And because of that, it's a little bit more challenging. And for the past 50 years, ESC and Spectrum have successfully addressed nearly every reporting issue identified through these regulations. We've grown, we've existed, we've expanded, we've matured over these years. And we're doing a really good job of helping our customers. And we try to help our customers make sense of and comply with the regulations, with the products and services that ESC and Spectrum offers our customers. Thank you.